Hey, what's going on, y'all? So we got a 3D problem now. This one says analyze the space truss. So the truss is composed of 4 nodes. In meters, the coordinates, right? And we got 3 elements with all the same cross-sectional area of 10 times 10 to the negative 4 meters squared. They give us the elasticity. They give us a force of 20,000 at node 1 in the x direction. And they also tell us that nodes 2 through 4 are pin supported. So they're all fixed in the x, y, and z direction. So it doesn't really ask for it, right? But we're gonna go ahead and find the stiffness matrix, the global stiffness matrix, solve for displacement, and then find the stresses in each element. So let's go ahead and get started. All right, so the first step in these problems, right, we got to find the length for 2 reasons, right? We want to get the stiffness matrix ultimately, which is this one right here. It's in 3D, so this is the first 3D problem that we do. But the book likes to call these little matrices lambda, so it's a 3 by 3 in this area, a 3 by 3 in this area, a 3 by 3 here, and a 3 by 3 here. And it's lambda, negative, negative, positive lambda. That's all it is. But these are the values right here. These are called direction of cosines, and it's symmetrical. At the end, you're gonna have a 6 by 6 matrix for each element. So this problem does get pretty tedious, but it's all good. It's nothing too crazy. As long as you know how to do 2D problems, you should know how to do 3D, as long as you follow these formats. And this is the formula we're gonna be using for the stress in each element. It doesn't say it right here, I'm not sure why, but the book solves for stress, so I'm gonna solve for it, but that's the formula we're gonna need here too. So in these problems, right, you start off finding the lengths, again, for EA over L and the direction of cosines. We're gonna need that later. So you do final minus initial. Again, I told you in every other video, right? You always go from from the small node to the big node. So in this case, for element 1, we're gonna go from 1 to 2, not from 2 to 1. For element 2, we're gonna go from 1 to 3. And then for element 3, from 1 to 4. So element 1 is gonna go from 1 to 2, right? Element 2 is gonna go from 1 to 3. These are nodes. And this one's gonna go 1 to 4. So just FYI, but we use the same principle when calculating the lengths. You do final minus initial. So length 1 for element 1, you're gonna do the change in x, which is 0, right? Final minus initial, 0 minus 12. So this is negative 12 squared, right? We're just following the formula up here. 0 minus negative 3, which is positive 3 squared, plus change in z. It's 0 minus negative 4, which is positive 4. If you do that math, you will get 13 meters, right? It's in meters, it says it right here, for length 1. So we're gonna cloud that up because we're gonna need these numbers, right? Same thing for element 2, right? So we know final minus initial, so 12, the x component, 12 minus 12, that's gonna be 0 squared plus, what else? Negative 3 minus negative 3, which is negative 3 plus 3, which is another 0 squared plus, last one, negative 7 minus negative 4, that's negative 7 plus 4, that is negative 3 squared. If you do that math, you'll get 3 meters for length 2. And then finally the last one, right, same thing. So now we're going 14 minus 12, that's gonna be 2 squared. 6 minus negative 3, that is 9 squared, plus finally 0 minus negative 4, that's positive 4 squared. All right, I guess it doesn't really matter if you do final minus initial here because you square them anyways, so, but it does matter when you get here. So just always be consistent, you'll be all right, okay? If you do the math here, you will get 10.05 meters for length number 3. All right, so second step. Before we start heading into direction of cosines, we want to get the stiffness for each element. So that's easy, right? It's EA over L, just like we've been doing. It's going to be in Newton per meter. Let's try to keep everything in simple terms, right? Newton meters. So in this case, it's 210 times 10 to the 9, right? Gigapascals for E. Area is 10 times 10 to the negative 4. And then length will change for each one. So they all have the same EA. Just the L is different for each one. So multiply this, 210 times 10, that's 2100, 2100, right? Times 10 to the 5th, because 10 to the 9 times 10 to the negative 4, that's just 10 to the 5th. So 2100 times 10 to the 5th divided by 13 in the first one, you will get 16.15 times 10 to the 6 to Newton per meter. For the next one, same thing, right? 2100 times 10 to the 5th divided by 3, you will get 70 times 10 to the 6. I just moved it one decimal over, so I'm getting 10 to the 6. In this case, it would have been 161.5 times 10 to the 5th, but it's just decimals, right? And then finally for this one, we will get 20.9 times 10 to the 6. All right, so now that we got that, we could go ahead and get the direction of cosine. So let me explain what this is. In 2D, we used angles. You remember? You got the theta, and you got the cosine squared, sine squared, all that good stuff. And we're still doing it, just that we're not using the angle anymore. You know how cosine is equal to adjacent over hypotenuse, SOHCAHTOA, right? That's all it is, right? It's just the distance between the x's divided by the hypotenuse length. And that's kind of what it is. There's more theory to it. It's not as simple as that, but I mean, I'm pretty sure you could care less. You just want to know how to do these problems. So this is the next step, direction of cosines, right? So we got, in the x direction, we will have the final node, x value, minus the initial node, x value, divided by the length of the beam. So L is different for each one, right? We got 3 different L's. So we're going to do this 9 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 3 beams. All right. So we can go ahead and do that, right? If you do, let's do the first one. XF, it's 0 right here, right? We're going from 1 to 2, so that means our final is node 2. So it's 0, the x component, 0, the 0 right here, minus 12. So it's negative 12 divided by 13. Negative 12 divided by 13, that's negative 0.923. Let's do another one, right? YF, so it's 0. Now this 0 right here, minus negative 3, that's positive 3, divided by 13 against the length for element 1. If you do that, you'll get 0.231. Do the Z one now, this one minus this divided by 13, you will get 0.308, okay? So that's that. Do the same for the other ones, right? Let's go ahead and do one more. I'll do the third one. That one's more complicated, so just in case. The second one's easy. So ZF, I'm sorry, for the third one, so it's this element right here, 14 minus 12, that's 2, divided by 10.05, that's 0.199. Now do the Y components. Final, right? 6 minus negative 3, that's 9, divided by 10.05. You will get, what was it, 0.896. Finally, do ZF minus ZI, so 0 minus negative 4. That's going to give you positive 4 divided by 10.05. You will get 0.398. So what I'm going to do now is I'm going to square this number and put it here, right? CX squared, CY squared, CZ squared. So I'm going to square all these and I'll put it here. I'm going to go ahead and give you these numbers. It's 0, 0, negative 1. That one's easy. So what we're going to do is square all these 3, put them here, and then we're going to multiply CX times CY. I put CXY, but I mean, oh, actually on this one, that was the only one, right? So my bad, messed up right there. So CX times CY. So you're just multiplying all these 3 to fill in the rest of the table. So I'm going to go ahead and just fill them up, and then we'll continue. All right, so I want to go ahead and fill that in. Verify these numbers are correct, but if you got something different, you're most likely wrong. So double check your answers because I'm pretty sure mine is right. Because I already did the problem. Okay, so that's the only reason I say it. But those should be the numbers you get. Make sure you understand how to do this piece at least. That's really important. That'll give you a lot of points on the exam if it comes up, but just FYI. So now we're going to go into the stiffness matrices for each element. Same thing, right? We're going to use this formula just like I mentioned. So now it's EA over L for each element, and then CX squared, CY squared, CZ squared. But hold on, this thing is huge to be doing it for every element. So it's important to start applying the boundary conditions right now as opposed to later, because you could save yourself a lot of time. So let's go ahead and do that. Nodes 2, 3, and 4 are fixed, right? They are pin supported and constrained from movement in the XYZ directions. That means U1, that's the X direction, V1, and W1, Y and Z directions, right? They're 0, 0, 0. Same thing here, U2, oh, U3, I'm sorry, well, this was U2. It's real important, you gotta be careful. U3, V3, W3, they're all 0. Okay. And U4, V4, W4 is also 0. Now it's good because we could go ahead and start applying the boundary conditions before we start filling in the table. So let's go ahead and continue, right? This is the formula we're using. I'm going to move it up. So it's EA over L for element 1 in this case. We already determined that up here. It was 16.15 times 10 to the 6. So I'm going to go ahead and do this. 16.15 times 10 to the 6, right? And this is from U1, V1, W1, right? From nodes 1 to 2. That's element 1. So it's U2, V2, W2. Same thing going this way. U1, V1, W1, U2, V2, W2. Cool. All right, now let's go ahead and go to element 2. We'll apply the boundary conditions in a second. We could go ahead and fill in this table, right, if we really wanted to. We already have all our CX, CYs, whatever, and we just plug in the table right there. But let's go ahead and continue doing the next element. For element 2, stiffness is 70 times 10 to the 6, as we determined, right? 70 times 10 to the 6, and that is between nodes 1 and 3. So we're going to go U1, V1, W1, U3, V3, W3. Same thing across, U1, V1, W1, U3, V3, W3. All right, finally, last one. Third element has a stiffness of 20.9 times 10 to the 6. So that's going to be like that. And again, we go from 1 to 4, nodes 1 to 4. So we're going to start U1. You always start with whatever node you start here. So if we would have went from node 4 to 1, we would have put U4, V4, W4, and then U1, V1, W1. But in this case, we started from 1, and we're going to 4, V4, W4. And finally, right across, U1, V1, W1, U4, V4, W4. So let's go ahead and apply the boundary conditions just like we mentioned. U2, V2, and W2 are 0. So let's go ahead and do this table. That's 0, that's 0, that's 0, and across 2, right? Row column. So that's 0, and this is 0. So we only care about these 3 spots in this matrix because 1 is, it's free to move in any direction. So that's why we can't cancel those out. U3, V3, and W3 are 0. So these go away. Boom, 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 and boom. Finally, U4, V4, and W4 are also 0. So these get canceled out here. So you see what I'm saying? We saved ourselves a lot of writing. All these numbers we would have filled in. It's better to apply your boundary conditions as soon as you can, especially in 3D problems. In 2D problems, I didn't want to confuse you guys. So if you saw the videos, I went all the way just to kind of show you guys what's happening. But now I'm assuming you understand FEA, so you'll be all right. Cool. So that means in this matrix, look, this matrix, this is a 6x6 matrix up top, right, where I'm writing. This is the formula, if you want to call it, right, what you should follow. So this is also a 6x6. So normally you would have plugged in every single value into here, but now we only care about the first 3 columns, rows, and rows and columns. Okay, so we only care about this 3x3 matrix right here. So that's it. That's all we fill in. So we know our CX squared or CY squared or CZ squared for element 1, right? We're on matrix 1, and CXY, CYZ is CXZ. So yeah, we could go ahead and start filling it in. So CX squared was 0.852. CY squared was 0.053. CZ squared was 0.095. And next one, CXY, that was negative 0.213. Next one, CYZ, was 0.071. And CXZ was negative 0.284. And it's symmetrical, so these come down as columns, negative 0.284. And this is 0.071. Now I'm gonna go ahead and fill in the rest, right? For this one, let me go ahead and do this easy one. This is cx squared, cy squared, cz squared, 0, 0, 1. So it's 0, 0, 1. Then we got 0, 0, 0, 0. Now I'm just following this formula. And again, we're only concerned with this matrix up here. And then finally, cxz is 0. So all these are zeros. It's symmetrical, so the rows become columns. Okay, that's all it is. And yeah, you know what, I'll just go ahead and continue it, right? We're pretty much here. So cx squared is 0.040 for element 3 now. 0.803 for cy squared. 0.158 for cz squared. Then we got cxy. And then we got cyz. Hopefully I don't confuse you guys with all these letters I'm saying, but I kind of already know what to do. Just make sure, it's pretty simple, right? Just using this matrix down here to plug in anything you see up there. It's pretty straightforward stuff. There you go. All right, so now what we're gonna do, normally we would go ahead and add the matrices, but we cannot do that because they do not share the same stiffness. So what I'm gonna do is I'm gonna multiply this 6.15 into here, this 70 into here, this 20.9 into here, and that should leave 10 to the 6 all by itself on all of them, and then we can add them up. So I'm gonna go ahead and do that, but I'm just gonna multiply 16.15 times every single number here and replace it with that. So 16.15 times this, erase this and plug in the new number, and etc. just for everything. But here you go. All right, so there you go. I just multiplied everything in. Right now that I did that, I'm gonna go ahead and erase the outside numbers, and you can verify these numbers, right? You should verify these numbers, but again, I am correct. So if you do not have what I have, then you messed up somewhere. But I just multiplied all the numbers into the matrix. So now they all have the same 10 to the 6 outside. So that means I could go ahead and add these matrices together, right? All the U1s, that one, this one, and that one, and come up with another 3x3 matrix. It's called your global stiffness matrix. So let's go ahead and do that. I already have it pre-written here, but same thing here, right? I'm gonna go ahead and apply the boundary conditions. So all this gets canceled out. U2, V2, W2, U3. I'm gonna go a little fast, so it might look nasty, but all these are gone, remember? So we don't care about any of this. And similarly, right, we're gonna go ahead and cancel all these. Doesn't look that bad. Thought it would come out worse. Kind of rushing it, but okay, that one did come out bad, but it's all good. We just care about these three, right? So we're gonna go ahead and add the positions at U1. So it's 13.76 plus 0.84 plus 0. Let me go and flip my paper. If you do that, you will get 14.6 for the first point right here. Now let's go ahead and do the next one, right? We're gonna add negative 344, 374, and 0. That should give us a nice 0.3. I'm gonna go ahead and do one more, right? Negative 459, 166, 0. Add them all three, you will get negative 2.93. Now I'm gonna go ahead and fill in the rest. You can go ahead and do them again. I'm right, so just verify you're correct too. Now another way to check it, I've noticed, I don't know if this is the case for all of them, but it's something I just noticed recently. The matrix should be symmetrical. So look, the one we're getting right now is perfectly symmetrical. You remember how the rows become columns? This row is this column. So that's what I've been noticing. I don't know if that's the case for every single problem, but I guess that's a cool way to verify you're doing something right if you get that pattern. But yeah, that's the matrix, okay? So now we're gonna go ahead and apply the force boundary conditions. So right here, it says we have 20 kilonewtons, so 20,000, right? We care about newtons, is applied at node 1 in the global x direction. And that's it. There's nothing else in the y or z. So we're gonna have this, check it out. We're gonna have a lot of erasing, but it's 20,000 positive, right? And then 0 and 0. So now we have 3 equations and 3 unknowns. So we could go ahead and start assembling those equations to find our u1, v1, and what do you call it? w1, right? All right, so I'm gonna go ahead and divide 10 to the 6 to 20,000. Well, to all 3, right? But these are 0, so it's just 0. But if you divide it by 20,000, you will get 0.02. That gets rid of the 10 to the 6 here. So we're eliminating that already. Now we have 14.6 u1 plus 0.3 v1 minus 2.93 w1. Okay. Next equation, we have 0 is equal to, I'm assuming you know how to do this, so I'm just going to go ahead and speed through it, but 0.3 u1 plus 17.72 v1 plus 8.65 w1. Finally, last one, 0 is equal to negative 2.93 u1, right, plus 8.65 v1 plus 4.85 w1. All right, for those that don't know, I'm gonna go ahead and explain it. It's just set this number equal to 14.6 u1 plus 0.3 v1 minus 2.93 w1. That's all it is. Okay. I don't know, it was just on my head. I had to let you guys know. But step 7, this is what we're gonna do. So this is algebra at this point, but I'm gonna go ahead and show you because this could be a potential on the exam, no calculators allowed problem. So I'm gonna go ahead and show you how to solve this, right? So trick is you're gonna do this twice, this method twice, and you have to use it with different equations. So in this case, I'm gonna use the first 2 equations, then the next case, I'm gonna use 2 and 3. So in this case, 1 and 2, then 2 and 3. But let's start with 1 and 2. So 1 and 2, let's go ahead and rewrite them, right? 0.02 is just systems of equations. So if you get up algebra, you'll be all right. u1 plus 0.3 v1 minus 2.93 w1. Cool, so let's put that in parentheses. And then next one, it's 0 equals to 0.3 u1 plus 17.72 v1 plus 8.65 w1. So we gotta get rid of one variable. It's easy to do it. So I like to use just the last ones just to get rid of them for some reason. It's always easier. So in this case, I'm gonna get rid of w. All right. So what I'm gonna do is I'm gonna multiply the top equation by the 8.65 and the bottom equation by 2.93. In this case, they will both be positive. Now, it's obvious to determine why, right? If you remember algebra. These signs are already contradicting each other, negative and positive. So if I multiply this positive to this negative, that's a negative number. If I multiply this positive to this positive, that's a positive number. They're the same number, right? 2.93 times 865, 865 times 2.93, same thing. They will cancel out, and you can go ahead and add the equations. And we're gonna do that twice, okay? So let's go ahead and do that. If you do the top part of the equation, 0.02 times 8.65, that's gonna give you 0.173. And that's going to equal to 126.29. Let's put 30, whatever. You'll be all right, don't trip. I'm going to go ahead and assume it was 29. I don't feel like erasing. Plus 2.6 v1. Oh, man, it's going to bother me. Ah, shit, whatever. All right, I'm going to go and put 29. Okay, so that's the first part. Now, the second equation. What is it? 0 is equal to 0.88 u1 plus, I'm just multiplying 2.93 times everything in here, okay? 51.92 v1 plus 25.34 w1. So we're gonna add them, right? These will cancel out. So that means you get, add the equation shit. I can't neglect that one. 173. 126.29 plus 0.88. That is going to give you 127.17 u1 plus 54.52 v1. So I'm going to cloud that up because we're going to need it. And like I said, now we're doing the same thing, but with equations 2 and 3. So I'm gonna go ahead and pause it and continue later. All right, just real quick, I just noticed this should have been a 74.85 because when you add them, my bad, 1.53, 332 plus 70. I forgot that 70 because these were all zeros, so I just been forgetting. But that's 74.85, and this is 74.85. Okay, just FYI. I'm glad I caught it, and I feel messed up because I was over here telling you guys were dumb if you didn't get what I got. But my bad, I was dumb. It's cool. Well, actually, not really. Hopefully, I didn't mess you guys up too much. But you should always check the comments before you watch any video, just in case I do a mistake. I usually catch it and I put it in the comments. But I did the same thing as I told you guys, right? Step now equations 2 and 3. So in this case, we use 1 and 2, 2 and 3. Same thing. I wrote the equations down. This is 2. This is 3. Focused on W. So in this case, they're both positive. So one of these had to be negative. In this case, I just put negative 74.85. So all this became negative, right? When you multiply negative 74 to 0.3, you get this. To 17.82, you get this. And to 8.65, you get this. Same thing, now 865 to all the bottom ones. The second equation, equation 3, you'll get negative 25.34 when you multiply to this. To this one, you'll get 74.82. And to this one, you'll get positive 647. Now the W's cancel out, and you add the equations. So negative 22 minus 25, that's negative 47. Negative 1326 plus 74, that's negative 1251. And that's it. You have 2 equations now, 2 unknowns. That's the whole point we're doing this. Now we're going to do that trick one more time. We're going to multiply this and this. This one's 54.52, so 54.52. And the top is 1251.52. Just mix and match, okay? This one's negative, this one's positive, so that means these have to be the same sign. Okay, you can do negatives, you can do positives, just keep it positive. I don't know why you would change it up, but so yeah, now if you multiply the first equation, let me go ahead and do step 9. I'm gonna write step 7 and 8. Okay, move it up. What else, so cool, multiply that. On the first part, you'll get 216.51 when you multiply 173 times 1251, you'll get that number, equals, and the rest to these two and these two, you'll get 155.8 U1 plus 68232.9 V1. On the second equation, right now this one, we will get 0 is equal to negative 2606.06 U1 minus 68232.9 V1. Add the equations together. Let's go here, step 10. You will get, add these two, 216 plus 0. That's going to be 216.51 equals, now 159,000, whatever that is, minus 2606. You're going to get 156,549.74 U1. Solve for U1, you will get, what is that? Our answer, 0.001383 meters. And use V1 to any of these equations to get V1. You will get negative 0.1234053 meters. And then W1, you will get 0.123406 meters, so 0. And that's your answer for displacement. I'm going to tell you guys something that sucks. If you would have rounded this to 138 only and not included that 3, you would have got negative 0.46. And this one would have also been 46, but positive. Now, it sucks, yeah, because that's I guess it's it shouldn't really be wrong. Yeah, technically you're off by, right, what's 5 over 4? That's like 80% of this number. But think about it. This is a really small displacement. Negative, if you move it 3 decimals, you're right here. That's half of a, that's not even, okay, so it's a tenth of a, half of a tenth of a millimeter. Does that make sense? So up to here, that would have been 1 millimeter. There was a 1 here. But it's not even 0.1 millimeter. It's half of that. So it's very small. Your professor shouldn't dock you points. It sucks, but I mean, sometimes some professors are so focused on the actual number That's what sucks when you start going into all this extreme, I don't even know what to call it, right? Just some crazy rounding. But yeah, that's the answer. Hopefully your professors are cool with it. Now let's go ahead and find the stresses. So we use this formula, right? It's E over L. This has a value, units of Newton per meter cubed. This is dimensionless, right? It's distance over length, so it's just distance over distance, so it's dimensionless. And this is meters, distance, right? It's a displacement vector. So Newton per meter cubed times a meter will give you Newton per meter squared. So that's just FYI. Now we need the E over L for each element. So let's go ahead and give you those. I'll show you right here, sorry. I'm gonna go ahead and write them right here. So E over L in Newton per meter cubed. I was gonna write it in this table, but for some reason I didn't squeeze it in. It's all good though. For element 1, that is just 16.15 times 10 to the 9. Element 2, that is 70 times 10 to the 9. And I'll show you how I got these, give me a second. Element 3 is 20.9 times 10 to the 9. Now check it. It's just easy, right? It's E over L. So it's 210 times 10 to the 9. Forget about the giga for now. Just 210, focus on it. 210 divided by 13, that's 16.15. 210 divided by 3, that's 70. 210 divided by 10.05, that's 20.9. And they're all gigapascal. Well, it was gigapascal, Roger, but it's just 10 to the 9. So that's all we got. So we can go ahead and do the formula. This is the formula I'm using. The bottom one, like this. Okay. So for the first one, sigma 1 is equal to the first E over L, which is 16.15 times 10 to the 9. Cx, Cy, Cz. Check it out. Sigma 1, we're doing the element 1, right? It's between nodes, what was it? Do you remember? 1 and 2. From 1 to 2. Now, in all cases, we're going from 1 to 2, 1 to 3, 1 to 4. So in all cases, we're going to have this value right here. This is going to be U1, V1, W1, U2, V2, W2, and then the next one's going to be U3, V3, W3, U4, V4, W4. But U1 is always first, these three. So check it out. I mean, we could go ahead, since all these are zeros for U2, V2, W2, and same node 3, same node 4, right? So that means all these are always 0. So we don't even care about these right here because they're going to get multiplied to 0. So we only care about these three and U1, V1, W1. Does that make sense? Because all the other displacements are 0. So you could go ahead and populate it just like you would, right? 0, 0, 0. But, I mean, you're going to multiply all these numbers to 0 anyways. It doesn't matter. So we're just going to go ahead and do this. So it's negative Cx, negative Cy, negative Cz for element 1. So it's Cx, Cy, Cz, but they're all negative, so all the signs switch. So it's going to be positive, negative, negative. 923, 0.923, negative 231, and what was the other one? Negative 0.308. 308. And now it's just U1, V1, W1. That's all it is. Okay, went a little too much right there. And we have them right here. So it's gonna be sigma 1 is equal to 16.15 times 10 to the 9, right? Nothing's changed there. So it's 0.923 times this number. What do you get? Let me flip my paper around. You will get 923 times the U1. That's gonna be, oh, it's because it's 923 times U1, then that, then that. Okay. So 923 times U1, that's gonna be 0.00128. And then it's going to be a positive because it's a negative times a negative. For that one, that's going to be 0.0000122 plus, oh, I'm sorry, it's a negative. So it's negative times positive. So it's negative 0.1234185. Add these three up, multiply it times that. Sigma 1 will be, what is that, 20.57 megapascals. Okay, so let's go ahead and do the other one more. I'm not gonna go fully, just in general, right? So E over L for the second one, what was it? 70 times 10 to the 9, right? So 70 times 10 to the 9, same thing, right? We only care about the first three, so CX, CY, and CZ just switch signs, 0, 0, 1. Oh, it's negative CZ, remember? Formula. So it's 0, 0, 1. And then U1, V1, W1. First two are 0, so we don't care about U1 or V1, but we care about 1 times W1. So sigma 2 is equal to 70 times 10 to the 9 times, let's see, what's that gonna be? It's just W1, that's it. 0.00006. Sigma 2 is equal to 4.2 megapascals. Awesome. Finally, I'm gonna let you do sigma 3 on your own, but just follow the same steps I've been doing, right? You will get negative 5.26 megapascals. And yeah, that should be your answer. All right, that should tell you. All right, so that's your answer, right? So sigma 1, it's positive, and sigma 2 is positive. So that means they're in tension. Now, you kind of really can't verify these logically. Well, you can only verify one of them, and that's the first one. So in this case, right, we're pulling with positive 20,000 in the positive x direction. So you can see how element 1 would be in tension. But you really kind of can't see it for element 3 and 4. Unfortunately, you just got to trust your gut, but at least we could verify one of them. Sigma 1 does make sense, right? And that should be 20 point, well, I don't know if it should be, right? But it makes sense that it's positive. I hope that makes sense. But yeah, that is the problem. This one was pretty long. I'm gonna do 2 more 3D problems. Make sure you guys know how to do those. We never covered it during class, but I had to learn this stuff just for you guys. So hopefully I helped in some sense, right?